La diffusion vient de démarrer. Tous les participants sont en mode écoute seul.
Hi everyone. Let me first tell you how happy we are to see so many of you gathered for this webinar on the topic that we choose to present today. Note that there will be a question period of approximately 15 minutes at the end of the webinar. During the presentation, you can please write your question in advance in the questions box at the right of your screen. Now, I'm giving the floor to my colleague who have kindly agreed to speak to you about this subject today. Louis Marcel is a civil engineer with RockTest for 25 years. Quickly introduced to the pressure meter test, Louis developed a great passion for this field of activity. His 25 years with RockTest gave him the opportunity to gain expertise in all aspects of pressure meter, from the design and manufacturing to the actual test and the use of their results. Thank you for your attention and enjoy the webinar.
Thank you, Jennifer. Good morning. I'm Louis Marcel, and I'm here to present this morning's webinar on the pressure meter testing. This webinar is the first of 3 webinars that will focus on this topic. Today, I will describe the different types of pressure meters and some techniques for performing the test. Note that I will focus on pre-board pressure meters. The next session will cover the interpretation of the test results and the main applications. Finally, the third and last part of this series will deal with the specific case of tests in rock. But first, a few words about RockTest. Part of the Nova Matrix group, RockTest was founded in 1967 in St. Lambert, Quebec, Canada. With manufacturing facilities in Canada and Switzerland, we have a presence in over 100 countries worldwide. RockTest has 2 lines of products. First, the geotechnical and structural instruments using vibrating wire and fiber optic sensors like piezometers, extensometers, and strain gauges. And second, the soil and rock testing equipment. Pressure meters are included in this second category. RockTest has developed a good expertise with this type of equipment by developing, manufacturing, and selling pressure meters for over 50 years now. Actually, RockTest played a significant role in the introduction of this type of test in North America. We now manufacture 7 different types of pressure meters. And now let's start with the presentation of the test itself. The pressure meter test, or PMT, is defined in the ASTM D4719 standard as an in situ stress strain test performed on the wall of a test cavity using a cylindrical probe that is expanded radially. The stresses are applied on the ground with pressurized fluid through a flexible membrane, which is covering the pressure meter probe. The aim of this test is to obtain information on the stiffness and on the strength of the ground by measuring the relationship between the radial pressure applied to the ground and the resulting deformation. We see at the right of this slide an example of a pressure meter. This equipment typically consists of a control panel that is used by the operator for applying the loads and taking the readings. Then there's a means for building up the pressure. In this case, it consists of a compressed gas. And finally, we see the probe that is inserted in a borehole and that is connected to the control panel using a tubing. The results obtained from a pre-board pressure meter test typically looks like this. The test is performed by progressively loading the ground by steps. At each step, there's a stabilization period before recording the data. On this graph, the first portion of the curve at the bottom corresponds to the moment when the inflatable membrane of the probe makes contact with the borehole walls. During the second phase, the contact between the membrane and the ground is well established, and we have what is called a pseudo-elastic zone, which is characterized by being quite linear. And finally, over a certain pressure, the ground appears to yield and enters into a plastic phase. This sequence of loading may vary depending on the type of pressure meter, the type of ground, and depending which standard is followed. Unload and reload cycles are often performed. Typically, a test lasts 10 minutes. Note that other special tests can be performed, like creep tests. At the bottom left, you can see the reference numbers of standards about pressure meters. Pressure meter tests are normally carried out at different depths in the same borehole. The results are typically integrated to give a stiffness and strength profile of the soil. Common spacing between the tests varies from 1 to 3 meters. The borehole should not be made in a single pass, but in steps. These steps consist in drilling the borehole to the first test depth, removing the drilling equipment from the borehole, lowering the pressure meter probe to the test depth, running the test, removing the probe, and then this process is repeated for each test. This way of doing ensures a minimum remolding of the ground. And following this procedure, about 4 to 8 tests in the same hole can be done per day. But this number varies a lot, may vary depending on the test depth, the loading sequence, the type of soil, and the experience of the crew. When doing a pressure meter test, it is assumed that the probe expands uniformly. So a flexible membrane should be used, of course, and the test should be done, possible, in a uniform soil layer. So it is important to pay attention when putting the probe in place to make sure that it will not straddle 2 different zones. Pressure meters can be categorized according to the insertion methods, and the type of probe, and whether they are designed for use in soil or in rock. Regarding the insertion methods, there are pre-bored pressure meters, self-pouring pressure meters, and cone pressure meters that are also referred to as full displacement or pushed-in pressure meters. Pre-bored pressure meters require making the borehole before inserting the probe. Self-pouring pressure meters are different. The probe includes cutting tools that will allow to make the borehole and to insert the probe at the same time. Cone pressure meters are simply pushed or driven directly in the soil. Now, the type of probes. We have the hydraulic probes and the electronic probes. The hydraulic probes contain no sensors. The deformation of the ground is measured by measuring the volume of fluid that is injected in the probe from the surface. So in that case, we talk about pressure meters based on the volumetric measurement principle. With the electronic probes, it's a bit different in the sense that the probe contains displacement transducers that will measure directly the radial expansion of the membrane. And this way it will directly measure the deformation of the ground. So we're talking here about pressure meters based on the radial expansion measurement principle. And finally, we have equipment that are designed for test in soil. Typically, we're talking about pressure meters or soil pressure meters, or in the case of equipment designed for use in rock, we're talking about rock pressure meters or flexible dilatometers. The great majority of the tests, of the pressure meter tests, are done using pre-bored pressure meters using hydraulic probes. We may note that the current standards about pressure meter only cover pre-bored pressure meters. So in this presentation, unless I specify otherwise, I will mainly refer to pre-bored pressure meters using hydraulic probes. The main parameters that can be obtained from pressure meter test are the pressure meter modulus, E, and the limit pressure, PL. The pressure meter modulus is a deformation, is a modulus of deformation that is typically measured on the pseudo-elastic zone. And it will be used typically for measuring the settlement or for estimating settlement or deformation of the ground. The second most important parameter obtained from the pressure meter test is the limit pressure. The limit pressure is, by definition, is the pressure reached when the initial volume of the test cavity has doubled. So at this point, the soil is considered having completely failed. The other parameters that can be obtained from a pressure meter test are the yield pressure, PF, that we see here. That is the moment where we see an apparent yielding of the ground. And there are other modulus that can be measured also. An unload-reload modulus can be obtained from an unload-reload cycle. A shear modulus can be calculated or can be obtained also, and a Young's modulus. Finally, there are other parameters like the creep factor N that can be obtained from a special creep test. Classical soil parameters can be estimated from pressure meter test also, with more or less reliability. The most common ones are the undrained shear strength, the horizontal in situ stress, the cohesion, and the angle of friction. And finally, on this graph, you can see the typical shape of pressure meter tests, whether you are using a pre-bored pressure meters, a self-boring pressure meter, or a full displacement pressure meter. But these aspects will be discussed in more detail in the session 2. Now I want to say a few words about the modulus of deformation. I think it is important to note that the modulus of deformation is not a parameter like the others in the sense that it can be affected by 3 factors. First, the soil conditions, then the sequence of loading, and finally the insertion method. So whether the soil is saturated or not, or depending on its level of consolidation, the value of the modulus will be different. The sequence of loading is very important also. So for instance, if you take just a few minutes to run the test and to yield the ground, or if you take 1 hour, you will end up with a modulus that will be different. Also, the stress and the strain level over which the modulus is measured will have an impact on the value of the modulus. And finally, if you run unload-reload cycle, if you repeat these cycles, the value of the modulus will also change. So it is good to try to follow a standard when you're doing a pressure meter test, or at least it is important to specify the loading method that was used. Finally, the insertion method is important, coming from the fact that when the probe is inserted into the ground, it will disturb the ground to some level. And this disturbance will affect the modulus. Typically, normally, the level of remolding should decrease from cone pressure meter to pre-bore pressure meter to soil, to self-boring pressure meter. But note that a certain level of remolding is almost always inevitable. So when presenting a modulus on a report, it is important to specify how it was measured. The pressure meter test can be used for a number of applications. Typical applications include the estimation of bearing capacities and settlement for shallow foundation especially, but also for deep foundations. The pressure meter tests can be very useful also for the design of laterally loaded foundation. Can be used for controlling ground improvement work, and it will be used for estimating the stiffness or the modulus of deformation of rock mass. So it can be very useful for the design of large structures on rock. And finally, it can be used for slope stability analysis, but this application is not as frequent. Now let's talk about the equipment. As mentioned above, different types of pressure meters are available. Knowing a bit more about these types can be useful for selecting a model that is properly suited to a specific situation by better understanding the differences regarding the special features related to their use and to the results they generate. So I will try here and in the following session to describe and to clarify these differences. I will now explain how these pressure meters work, starting with the most commonly used models in North America and moving on to the less commonly used ones. First, let's start with the TEXSAN model, which uses an hydraulic monocell probe. This equipment is pretty simple. It works a little bit like a syringe. So the control box contains a cylinder filled with water in which there's a piston that can be activated using a screw jack. The operator simply crank a handle in one direction or the other direction for pushing or pulling water from the probe. This equipment uses an hydraulic monocell probe. We see one here that is fully assembled. And we see the component of this probe. We see the body of the probe here, and we see the sheath and the rings that are used for assembling the sheath on the probe. So when we saturate this probe, we fill up the annular space between the sheath and the probe's body here. There are different types of sheets that can be used. We may use plain rubber sheet or reinforced rubber sheet, but the most common sheet in North America are what is called the metallic sheets. This sheet consists of a rubber tube that is covered with metal strips. These metal strips will protect the rubber from being punctured by any sharp particle that can be in the soil. But at the same time, these metal strips will not prevent the probe from easily expand when it is pressurized. The second most common type of pressure meter here in North America is the Menard Passion. This pressure meter is characterized by using two circuits, a gas circuit and a water circuit that are used at the same time for inflating the probe. The probe is a hydraulic tri-cell probe. It has two sheets, an outer and an inner one. The inner sheet is inflated with the water circuit. This is in fact a measuring cell that is used for estimating the ground deformation. The outer sheet is inflated with gas. On these images, we see the probe uninflated, the probe inflated with gas only, and the probe inflated with water only. During a test, the probe must be inflated with both gas and water. But the pressure of the water circuit should always be higher than the one in the gas circuit by a constant value of 1 bar. This is for making sure that the inner sheet remains in contact with the outer sheet and for making sure that the inner sheet does not extrude at both ends. This will allow the measuring cell to reliably measure the ground deformation. This system was developed by Menard in the 50s in order to mitigate these end effects that would otherwise bias the pressure meter measurement. You may now think that this compensation system is not present with the volumetric monocell probe. You're right. But in that case, researchers like Jean-Louis Briot have shown that if the measuring cell of the probe is long enough, if it exceeds a length to diameter ratio of 6, these end effects will become negligible. So that explains why the hydraulic monocell probes are longer. On this slide, you can see an entirely automated version of the Menard Passion. For using it, you just need to set up the test parameters and you launch the test. And the test will then automatically be done by the machine. The two types of pressure meters I've just described are pre-board pressure meters. Pre-board pressure meters have the advantage compared to self-pulling pressure meters and full displacement pressure meters that they can be used in almost all types of soils, as far as you're able to make a proper borehole first. Unfortunately, it is not always possible, especially in soils that are heterogeneous, in soils that contain loose sands, gravel, blocks, and boulders. So in these cases, the drilling methods should be adjusted. But sometimes the only option is to use a slotted casing. A slotted casing is a steel casing, you see one here, is a steel casing that is fitted with longitudinal slots from here to here that you don't see now, but because they are so thin and the casing is closed. It is also fitted with a conical point. So for doing a test, you have to insert a smaller size pressuremeter probe into the slotted casing, and then you pressurize the probe. And thanks to the slots in the casing will expand as the probe is being pressurized. The casing will prevent the probe from bulging in any voids, if there's any void in the borehole. So this system will allow testing difficult soil, but it should be used as a last option because it may be difficult and time consuming. But at the same time, some users developed a very good expertise with this equipment, especially for testing fields. On this slide, you can see a full displacement pressure meter. You see the model pressure, the tensile pressure meter. This pressure meter uses an hydraulic monocell probe having a small diameter and fitted with a conical point. So this allows to push the probe directly or to drive the probe directly into the ground. This model of pressure meter uses the same simple syringe-like working principle as the TEXSAN. It is ideal for remote sites, for shallow foundations, and also for compaction control. Here we have an electronic monocell probe. So we see here a probe that is disassembled. We see the sheath, the rings, and the body of the probe. And we see that at the center, around the center of the body of the probe, there are displacement transducers that are spring-loaded. These will always remain in contact with the sheath and will follow the radial movement of the sheath. And these are positioned in a different direction. Some models are very sophisticated and will include other sensors, like pressure sensor inside of the probe for measuring the pressure in the probe, but also outside of the probe for measuring the pore pressure. Also, some model will include a compass for measuring the orientation of the probe. The probe can be inflated with either gas or liquid. Here you see self-pouring pressure meters. Self-pouring pressure meters were developed with the objective of minimizing remolding of the ground. Can be used in fine soils and sandy soils. Here you see how it works. You have the probe, and in the probe there's a cutting tool, there's a cutting bit, and a probe shoe here. And the cutting bit is connected to a drill rig through an inner rod. And there's also an outer rod. The outer rod is used for holding the probe, for pushing or pulling the probe, and the inner rod is used for injecting water and for applying some rotational movement to the cutting tools. The cuttings are evacuated through the probe up to the surface. We can see here at the right the more simple model using a hydraulic probe. And here at the left, an electronic model of the self-pouring pressure meter probe. On this table, I tried to summarize the main strengths and weaknesses of each model of pressure meters. So first, you have the Menard tri-cell hydraulic pressure meter. This model is interesting. It was the first pressure meter that was developed, and it is the model that is the most used worldwide. So there are a lot of references regarding this type of pressure meters. And what is interesting about this equipment is that special design methods were developed over the years based on this model of pressure meters. Now, the main weaknesses. First, it requires a good preparation of the operator and of the equipment. It is not well suited for cycling tests, except the automated model. And also, the curve is not so well defined. It only has about 10 points. Then we have the monocell hydraulic pressure meter, which is the TEXSAN pressure meter. The TEXSAN pressure meter was developed in the 80s with the idea of providing a pressure meter that would yield results, test results that would be comparable to the Menard pressure meter results, but with an equipment that would be much easier to use and to maintain, and that would be rugged and safe because not using any gas. So these are important features. Also, this equipment is very versatile. Can be used for running strain or stress control tests. It can be used, it is easy to proceed to unload and reload cycles. And also it is compatible with some self-boring probes and cone pressure meters. However, since it uses a monocell probe, there is some slight potential end effects, but these would be negligible considering that the probe is long enough. Also, water is required in the borehole for running the test. Then we have the electronic probes. The main interest of these probes is that the deformation and the pressure are directly measured in the probe. So this allows some high resolution measurement and also high acquisition rates. Also, some models are very sophisticated, as I already mentioned. And finally, it can be used in dry boreholes. However, this type of pressure meter is more delicate. The fact that the probe contains electronic sensors may cause some problem, especially when the membrane bursts. And this happened once in a while. And when this happens, the electronic sensors can be damaged and it is hard to repair. So. Also, this equipment does not measure it will measure, take a measurement at a specific point at the center of the probe. So it will, some will argue that it is better to have an average measurement over the entire length of the probe, as volumetric probe gives. So. And finally, some of these models are less commercially available. Then you have the self-boring pressure meters. The main advantage, of course, is that this model can reduce remolding of the ground if it's properly inserted into the ground. Also, it is better suited when using indirect design methods, which is for estimating some soil parameters. However, this equipment is pretty difficult to use. All the adjustments that must be made during drilling, and insertion of the probe can be difficult. So it requires a lot of experience for handling this equipment. Also, it is confined only to some type of soils. There are also some depth limitations, and overall, it is not used very often here in North America. And finally, you have the full displacement pressure meters. This model is interesting because it allowed to run more tests in a single day. Instead of running 2 to 8 tests, you can run up to 10, 15 tests per day, if everything goes well, of course. Also, it can be used on remote sites, because where it is hard to bring a drill rig. Also, it can be used with the CPT probe at the same time. And finally, it mimics the effect of driven piles, which can be interesting for the design of these driven piles. However, it cannot be used if the soil is too hard. And also, you have to be careful, because the parameters you obtain from this test may be affected by the insertion method. Whether you drive or push the probe, or if you put it in a pilot hole, there might be some effects. But some will argue that this effect will be repeatable. So. This chart shows the different pressure meters depending on their range in terms of modulus and limit pressure they can measure. So you see here the small pressure meter, the pencil model that can be used in soils only if the soil is not too hard. The TEXSAN pressure meter can be used in almost all type of soils, but also it can be used even in soft rock, where it can measure modulus in blue here. But it cannot be used in soft rock for measuring strength parameters, because the maximum working capacity of this equipment is 10,000 kPa, which is not enough for yielding the rock. And completely at the bottom, you have the rock pressure meters, or the flexible dilatometers that are mainly used in rock. So that's it for the equipment. Now I will explain quickly how to run a pressure meter test. Again, I will focus on the pre-bore pressure meter test. On these pictures, you can see the main steps that need to be followed. First, you need to prepare the equipment. Then you need to drill the test cavity and insert the probe. And then the test itself can be done. Unfortunately, it's not always as easy as it looks. So after preparing the equipment, you need to calibrate it. There are 2 calibrations. First calibration is the pressure loss calibration. And this calibration consists in inflating the probe on confine and by measuring the resistance of the membrane. This resistance will be subtracted from the total pressure that will be measured afterwards during the test. This calibration can be done once when you put on a new membrane, and then it doesn't need to be repeated unless testing very soft soils. The second calibration is the volume loss calibration. This calibration consists in pressurizing the probe in a steel pipe and measuring the deformation of the equipment. This deformation comes from the membrane that will squeeze a little bit, and from the lines that will expand in the unit. And also if there's some air in the water, from the air that will compress. This deformation will also be subtracted afterwards from the total test results. And this calibration is also important because it will prove that the equipment is working properly. So it is good to repeat it often, almost every testing day. On this slide here, you can see the effect of this calibration over the test results. You have here in pink the volume loss calibration, the pressure calibration, where you see the resistance of the membrane that is really low. And in red here, you see the deformation of the equipment obtained from the volume loss calibration. And you see the effect on the raw readings in blue. That must be corrected, and the final result is in green, the corrected test data. Now, a few words about how to make the borehole. This step is very important. Actually, it is a critical step for making a good pressure meter test. There are two main requirements. First, the test cavity should have the proper diameter. The probe must fit pretty tightly in the borehole. The borehole should be a bit larger, but not too large. If the borehole is too small, the probe will be pushed into the soil, and this will disturb the ground. If the borehole is too large, it won't be possible to complete the test, and you will miss some information about the limit pressure. So by experience, we say that the borehole should be between 3 to 10% larger than the probe. So for an N-size probe, that is 74 millimeter, it means that the borehole should be between about 76 to 81, 82 millimeters. So you see that it's a pretty, there is no much tolerance. Also, the borehole walls should be smooth, so there shouldn't be too many voids. The second requirement is to minimize soil disturbance. So this is achieved by following the proper drilling method. It is better normally not to drive a split spoon for making a test cavity, or if you do so, keep in mind that there might be some effect on the value of the modulus that you will obtain. The importance of using a proper drilling method is shown by this table that is included in the ASTM standard. We see all the methods that can be used compared to the type of soils. And we see that there's one method that stands out from the other. It's the rotary drilling method with bottom discharge mud. And we see that this one is much more versatile. Actually, it can be used in almost all type of soil, except in sandy gravel or gravelly sand where it is not recommended, where the only option may be to use a slotted casing or a slotted tube. So the method that we suggest to use, that we really suggest to use, is the mud rotary drilling method with bottom discharge mud. We suggest it because it is versatile. You'll be able to test almost all type of soils if you do the proper adjustments. Also, it will keep the disturbance low. And finally, it is adapted to hydraulic probe that already requires a fluid in the borehole. Other methods can be used also, but they should be used only in specific soils. So flight auger will be often used. Hand auger could be useful, but it is possible only if you are running shallow tests and using a small probe. Shelby tube in the clay can be used sometime, and the slotted casing. So now I will talk a little bit about the mud rotary drilling method, since we really suggest to learn how to use this method. So first, it is important to use drill bits that has the same size as the probe. So for an N-size probe, you should use the 2 and 15/16-inch drill bits, up to 3 and 1/16 in cohesion-less soils. So you may keep different size of drill bits on sites to adjust it if you are for any variation in the soil type. A tricone roller bit is the most versatile tool, and 3-wing bits can be used or are very work properly in clay and silty soils. The bentonite mud is the best mud, I think, but other type of mud can also be used. Also, the drilling tools should have the proper diameter, so they should not be too big. So the cross-section of the drill bit and the adapters that is used and the rods should not be too large. They should be small enough to allow cuttings to go by. So the most common size of rod that will be used will be a size rod. Also, it is important to go slowly, what is not natural for drillers. So you see, we say here about 60 RPM. We say that you should work with a slow mud circulation. So because of that, it can take up to 20 minutes for making a 5-foot-long test cavity. So it is important for the driller not to hurry. Also, you should not perform excessive cleaning of the drill, especially in loose sands. So if you do so, you may end up with a borehole that will have a diameter that is too large. And it's good to have some rooms under the test depth for the cuttings to settle, if there's any cuttings. So also, it is good to make the borehole above the test zone slightly oversized. And it is important not to push the probe. You should not use the drill rig for pushing the probe in place. 2 drillers with a pipe wrench can push the probe, no more. So there's a learning curve for these drilling methods. So it is good to work with a drilling crew that has some experience, or at least to plan at least a day for learning all these or making all these adjustments. A typical method consists in advancing the borehole using a 4-inch casing or hollow auger to about 2.5 feet above the planned testing depth. Then the test cavity is drilled and the probe is lowered into the ground. You can see that it is a good thing to tape the tubing to the rod for protecting the tape. The test can be then performed, and this entire process is then repeated. And I mentioned here at the end that it's important to fine-tune the drilling technique based on the results of the test that was just done. I will now give a quick overview of the main steps for using the TEXSAN pressuremeter. I've chosen this pressuremeter since it is the most commonly used model here in North America. And in any case, many of these steps also apply to other pressuremeters. So first, you need to prepare the equipment. So to assemble, to fill the equipment, and to calibrate it. Then you have to make to drill the test cavity as described before, and you have to insert the probe into the test cavity with no delay. You have to record the test depth, which is the distance from the surface to the center of the probe. So you may have to measure all subs and rods that are used to make sure to know exactly where the probe is located. Then you start the test. The TEXSAN test is normally done using a strain control method, which consists in injecting 40 cubic centimeter of fluid and then to wait 15 seconds for pressure to stabilize before recording the readings. So this is the method B as described in the standard. It is important to check the data as the test proceeds to know where you are in the three zones, you know, of the test curve, to know when the probe is making contact with the borehole wall, and also to see if you are in the pseudo-elastic, the straight zone or not. So this is important. At the end of the straight zone, an unload reload cycle can be done. And there are different methods for doing these unload reload cycles. One method consists in simply start to unload when you see that the soil is starting to yield, and then by reducing the pressure in one step and reducing the pressure by half in one step, taking a reading and then going up and then resuming the test. Or it is possible to go lower to reduce the pressure to a point closer to the contact pressure and to go by steps. It is also possible to repeat these unload reload cycle further away during the test. But beware of the variability of ER, which is the modulus that is measured on these unload reload cycles. Because depending on how you perform these unload reload cycle, depending on the time you take for doing that and the pressure and strain range, all these elements will affect the modulus you will measure, you will obtain. Also, a special 10-minute creep test can be performed. It will normally be done at the end, past the pseudo-elastic zone, and it will consist in maintaining the pressure for 10 minutes and measuring the volume change every minute. Then this test must be stopped when you have enough points for estimating the limit pressure. This is where the curve is almost asymptotic with the volume increase, or the test is stopped when the maximum capacity of the probe is reached, which is 1600 cc for the N-size probe. But normally you don't reach this point. Tests will typically be stopped between 1000 and 1200 cc. And finally, the probe is deflated. Note that you have to deflate the probe by creating a negative pressure at the surface, so you have to crank slowly. If you go too fast, there's some air that can get into the unit. Finally, the probe is clean and the test can be repeated. The pressure meter test done with a Menard Passion is very similar to the method that I just described. But there are two main differences. First, with this pressure meter that has two circuits, you have to adjust the differential pressure. You have to make sure that there's always a 1 bar pressure difference in the probe. So this adjustment depends on the test depth, and it should be done before every test. The other difference is how the test is run. Menard Pressuremeter test is done by following the stress control method, which consists in having about 10 pressure steps until reaching yielding of the soil. So these pressure steps must be decided by the operator depending on how hard the soil is. So it can be from about 25 kPa in very soft soil up to 500 kPa in very hard soil. Also, readings will be taken after reaching each step. Readings will be taken after 30 seconds and 60 seconds. And the variation of the volume between these two readings will be allowed to plot a creep curve that we see here. This curve is not used for design purposes, but it allows to better spot the PF, the yielding pressure on the main curve. And now a few typical problems and solutions related to the pressuremeter test. First, is it possible to run a test if it's getting very cold? And that's the main issue here in Canada. Yes, it's possible, but of course you need to use antifreeze if you don't want to damage the unit. Or if it gets really cold, you can use a heated shelter. It is also possible to run a pressuremeter test if it's very hot, but it is important to protect the equipment from direct sun. So the use of a portable canopy is very good. It's good for the equipment and good for the operator. It is possible to run tests at great depths. Maximum would be about between 100 to 150 meters for the TEXSAN and Menard probe. But electronic probes using gas can be used in dry holes and probably deeper than this. A typical problem is when the membrane bursts too often. So if this happens, it means you have first to try to make adjustment to the drilling techniques. You have to make sure that the probe is properly assembled. And you have to make sure that the rubber membrane is not too old, because with time the rubber will lose some of its mechanical properties. You have to make sure that the flow of fluids is not too slow when using a Menard pressuremeter because of the cold temperature or because of dirt in the unit. So you have to make sure that the unit is very clean. And finally, you might have to use a slotted casing in difficult soil, or you may have to stop the test early. And some final recommendations related to how to run the pressuremeter test. First, it's a very good habit to prepare, and a good thing to prepare the equipment before going on site. So it will help to practice and also to make sure that the equipment is working properly, because you don't want to find out that on site that the equipment is not working properly. Also, we suggest to keep spare parts on site, especially 2 sets of probes. So if one membrane bursts, you can directly use the second set of probes. You have, of course, to pay a very close attention to the preparation of the borehole. You have to check the test results on site to make the required adjustments. This will improve the quality of the other tests that you will do. And do not mind about bursting some probes, some membranes. The average is maybe around out to 6 tests, but this number vary a lot. It depends on the soil type very much. So some soils, some homogeneous soil, clay soil are more easy to test, where you can run 10, 15 tests without having to replace the sheet. But in other type of soils containing gravel, the bursting rate will increase. And finally, a general understanding of the tests is a good thing. From how the equipment works, how to make the borehole, to how the probe is inserted, to how the data are reduced. If you have a general understanding of that, it will help to have to be successful. And also, it's good to have teams that are dedicated to the pressure meter tests. To conclude this first session about the pressure meter test, I will give the main limitations and advantages related to this type of test. First, there are different types of pressure meters and test methods and interpretation methods. So this can bring some confusion. And if you mix these, this could have an impact on the results. So you have to be careful. You have to select the equipment and the test methods, considering the soil type, the drilling tools you have, and the purpose of the test. The borehole should be done properly, of course. I said that many times. It is really important. You have to allow some resources for the training and practicing. Price and time can be an issue, especially if you compare this pressure meter test to the SPT test, for instance. In that case, you would think that a pressure meter test is much more expensive and takes more time than an SPT test. But it depends actually, because the quality of the results, the information provided by pressure meter test is more valuable. So it compares more to other type of tests, like large scale testing, for instance. So that's why I put a question mark here, because price and time could be seen as an advantage too if you compare the pressure meter test to large scale tests, for instance. And final limitation is that some soils are more difficult to test. Now, the advantages. An important advantage is that the pressure meter test is very versatile. Actually, it is the most versatile in situ test, in the sense that it can be used in almost all types of soils and rocks too. And also, it can be used for a number of applications. A second advantage is that it gives very good quality information. It provides information on both the strength and stiffness of the soil. Also, there's a close analogy with the laterally loaded foundations. So that makes a very good test for these type of foundations. The validity of the test can be controlled using some tools like the shape of the curve and some ratios like E/PL. And finally, the loading sequence can be adapted to the application. So you can want to run a creep test or cyclic tests, for instance, for the design of pylons or wind turbine, for instance. So these are the main advantages of the pressure meter test. So this completes part one of this webinar series on the pressure meter testing. I hope you enjoyed it, and thank you very much.
Excellent, Louis. Thank you for the presentation. We will now move on to some questions that some participants have asked. Let's start now by giving the floor to our colleague René Deblois, Sales Director at RockTest in Montreal.
Thank you, Jennifer. Thank you, Louis. A few good questions from the attendees. The first one would be, how long does it take to replace a membrane when it bursts? You mentioned about bursting, but how long it takes normally to replace one?
It depends on the type of probes. If you are using the probe that are the easiest one are the Monocell volumetric probe in the TEXSAN probe. In that case, if it may take about half an hour for replacing the sheath, but again, it depends on the experience of the operator. The first time it would take more time. In the case of the Menard probe, it's more about 1 hour because there are 2 sheets that needs to be replaced. And this can be done on site, but you need to have a bench device for doing that. So very often the people will do that in the evening when they go back at the office. And by the way, we have some documents and video explaining how to replace, and some documents also explaining how to make this to replace these sheets. So that's it.
Okay, thank you, Louis. Other question quickly. How long does it take, you think, for someone to become from a beginner to someone not expert but good enough with the equipment to be able to run the tests normally? Say, how long would it take for someone to become a good operator?
Yeah. Again, it depends on the equipment, on the types of pressure meters that you are using. I mentioned that there are some pressure meters are very sophisticated, but in the case of the most common pressure meter, the TEXSAN pressure meter, it takes at least, I would say, it's good for the operator to practice at the office, to get familiar with the equipment, to assemble it and to saturate it, to calibrate it. It's a good thing to take at least a day or 2 at the office doing that. And also for making the borehole, as I mentioned during the presentation, for the drillers, the first day it takes at least a day. So I would say that a couple of days are required for getting more comfortable with that.
Okay, thank you. And maybe one last question. You mentioned that it takes about 10 minutes to deflate a probe. One attendee mentioned that for monocellular types of probe, it takes about 1 hour. Did he or she take too much time, or is it something wrong? Or
yes, normally it should take about 10 minutes, but it is true that very often it will be a bit difficult. It is more. It will be more difficult, especially in flat clay and clayey soils where the probe will stick to the borehole walls. In this situation, you have to use some special tricks. you have to use the drill rig for pushing or pulling slightly on the probe, so it won't to get it unstuck from the borehole walls. Some users will apply some silicone oil also on the membrane when they are testing this type of soil very, very often. So there are some adjustments that should be made. But if you do so, normally, just about 10 minutes normally. And also, if the tubing that you are using is very long, this will add to the time for deflating the probe. So I would recommend not to use a tubing that is too long also. But there are a few things, some adjustments that are required. And if you are doing that normally, and also if the weather, if the temperatures, if it is cold and that you are using antifreeze, some types of antifreeze will get very viscous at cold temperatures. So you have to be careful. We recommend in this situation to use windshield washer liquid, because this type of antifreeze will get less viscous and it will be easier to deflate the probe. But in that case, you need to clean the equipment afterwards, because this type of antifreeze may be corrosive for the equipment if you keep it for a long time in the equipment. So that's a long answer. but I hope it helps.
Thank you very much, Louis. And the other question will be answered individually by email. Thank you.
Yes, thank you, Louis, for your answers. Unfortunately, time goes by and we appreciate all the questions you sent to us. We'll answer your questions directly to each one of you by email in the outcoming days. Thank you very much, everyone, for taking time today and showing interest in our webinar. Hoping we can collaborate in future projects together. So if you have any question or for more information, feel free to contact us. Again, thank you. It was a pleasure.